Okay, hello everyone. So today we are starting a new topic, work and energy, and these are the subtopics we'll be discussing. Work done by a force, a constant force, work done by a varying force, a force that is not constant, kinetic energy. It's another new topic. You guys already have heard about these terms, kinetic energy or the term energy. So we'll look into that, and then work energy principle. During the lecture there will be some sections that need calculus, so I will mention that. So those are only for university physics students, but I will mention when I'm using calculus or when it is not required for the college physics students. All right. Okay. So work. Let's start with talking about work. The physical quantity work. Now work is a very common term, a very common quantity in physics. We use the letter W, capital letter W, for work, and the unit, standard unit for work is joules. So joules indicated by J, and also there's another unit for work which is Newton meters, and joules and Newton meters are the same, they're equal. It's the same unit, just a different name. Now what is work, or how do you measure work? When you apply a force on something, some object, and if this force is able to move that object in the direction of the force, then we say that this force is doing work. So for an example, let's say, going back to the same box on the floor, here we have a box, some object, and then you apply a force F like this, and as a result of this force the object moves from this point A to point B. Right, now the box is here. So the distance it moved in the direction of force, let's say D, distance or displacement, we can use the letter X as well. So the work you do, you apply a force which is in newtons. As a result, the object moved a distance measured in meters in the direction, see, the force applied this way, it moved in the same direction to the right. The work you did, the work done by the force, is given by F times D. So F is measured in newtons, displacement or distance measured in meters, so Newton meters, which is also known as joules. So for an example, if you apply a force of 10 newtons to move this object, let's say there is no friction, it's a heavy object, but because there is no friction you can easily move it even with a small force, and it moved to a distance of 20 meters. So you keep this force constant throughout, from the starting point to the end point, right? You apply 10 newtons, it's moving, you continue to apply 10 newtons, still moving, applying 10 newtons. The object could be accelerating, that's fine, we don't worry about all these accelerations and all that when we are calculating work. It's only the force times distance. So as a result of this 10 Newton constant force, the object moves a distance of 20 meters. So the work you did is equals to force times distance, or we can write it as force times d. See, I'm switching between x and d so that you get familiar with both. Some textbooks use d, some use x. So 10 times 20, 200 Newton meters, or you can say 200 joules. Either unit is fine. Okay, so that's in very simple terms, this is how you find work. Okay, so the equation I showed you here, this is not entirely, this is not the complete final form, right? There's a little modification to this. So let's look into that. So I'm going to clear the whole thing. Alright, so let's go back to the diagram we had. So there's a box and you apply a force. We can apply the force horizontally. We can apply the force at an angle also. There is no rule saying the force has to be horizontal, right? The force can be any angle. So let's draw that. So that is that is a better form of representing this. So here's the horizontal line, here's the force applying with an angle theta, right? Applying the force horizontally is a special case. Here's a more general case. So if you make the angle 0, you get a horizontal force, or you can keep it at any angle you want. So this is more general. This is how the actual force equation, work equation is defined. So let's say you apply a force, and as a result of this force, the object moves a distance d. Now, when it comes to calculating work, it's defined as work equals force multiplied by displacement, but in the direction of applied force. In the direction of the force. It can't be in any direction. The distance we measured has to be in the direction of the force. Now the force is pointing upwards. It moves horizontally. So what we do is we take the component of the force, this xi and y component, so we can divide this into f. Now you guys already know this, f cosine theta and f sine theta. Now if we find work, force multiplied by displacement, but in the direction of the force. Now if you look at this y component, it doesn't do anything. The object does not move upward, it moves horizontally. So this sine theta component, the vertical component, doesn't do any work. It's just there. You can say it's a waste. What the component that really does some work is the horizontal component, or the cosine component. So we define equals to f cosine theta times displacement, which is d, and we switch the terms back and forth a little bit, rearrange the equation. Work is f d cosine theta. So this is the better final standard form. Work is equals to force multiplied by distance multiplied by the cosine of the angle between them. So if the angle is, now if you think about this, if the angle is 0, if theta is 0, cosine theta is 1. That means force and displacement in the same direction, right? Or you can have any other angle like 30 degrees, 40 degrees, like that. So this is how we find the work. All right, so let's try an example. Let's see, I'm taking these examples from the PowerPoint slides, which is available under files in your class Canvas page. It says a person pulls a 100-kilogram crate 50 meters along a horizontal floor by a constant force of 100 newtons, too many hundreds, which acts at a 30-degree angle. Okay, horizontal floor, 100 kilograms, the crate, move it to a distance of 50 meters. Crate is here. Applies a force of 100 newtons. 100 newtons, making 30 degrees with the horizontal. It says assume no friction. Okay, so and then the question is, what is determine the work done by each force acting on the crate. So the question is work. It's asking determine the work done by each force acting on the crate. Each force. What are the other forces you can think of? Now it has weight mg. There will be a normal force which is equals to mg. We can divide this 100 into components. 100 cosine 30 and 100 sine 30. Now once you do that, we can forget about this main force. Now we have these four forces, right? The cosine component, or the x component, the y component, the weight, the normal force. It says there is no friction, so there is no any other force. There's no frictional forces. So only four forces. As a result of this applied force, it moved to a distance of 50 meters horizontally. So the question one we should determine is, what are the forces that are really doing any work here? It moved 50 meters, but mg, the normal force, and 100 sine 30, they all of them are perpendicular to this 50 meters. If the force is perpendicular to displacement, then work is 0. In other words, there's a cosine theta. If the angle between them is 90 degrees, you know that if theta is 90, cosine theta becomes 0. Cos 90 is 0. So there's a 0 goes into this equation. W equals F times D times 0. The whole thing becomes 0. So these forces mg, n, and that sine component, right, none of them doing any work here. The only force that does work, that does some work, is 100 cosine 30, because the object moved in that direction. So what is 100 cos 30? Let's take the calculator, type in the numbers. 86.6. This is the only force that does some work. So the work is equals to it's f d cosine theta. Now we already took the cosine component, so therefore we don't have to put this again, right? So we already took that cosine into consideration. So therefore the answer is the force 86.6 multiplied by 50 meters, which is equals to 4330.12 Newton meters or joules, or you can say 4.33 kilojoules. Okay, kilojoules. All right, so let's try another example. So let me clear the whole thing. This time we have a hiker climbing a hill, going up a hill, and the question is how much work he has to do. So let's say this is the hill. So here's the hiker, and it says hiker is 60 kilograms. He has a backpack of 15 kilograms. So can't draw a backpack here, so I'm going to put the backpack on his head. That's 15 kilograms. So he wants to go up the hill to a height of 100 meters. 100 meters. So once he's up here with the back, head back, how much work he has to do? Now, you know that when you walk, when you climb steps, you get tired because you are doing work. Especially if you are climbing steps, climbing up some steps, you get tired very fast because you are doing work against gravity. Gravity is pulling you down, right? You are doing work against that. You are applying a force, and then that force moves against gravity. So that's what work is. That's called doing work. You spend energy to do work. You apply force. By spending energy, you apply force, and then you move that force to a distance so that you do work. Okay, so in this case, how to find the work? Now the total mass is 60 plus 15, 75 kilogram. That's the mass of the person. Now what kind of force he has to apply? So he's going this way. So we can make it very complicated and find how much force he has to apply in this direction, and then calculate this distance along the hill, which is not a straight line, it's kind of curved, right? So that's going to be even trickier, and multiply that weight component by the distance, you can find the work. But here's an easier way to do that. So if you think about the person with the mass, the total weight, so here's W for weight, but this W is for work, okay? So don't get confused with that. So let me just say G. His mass or his weight is 75, that's the total mass, multiplied by 9.81. What is 75 times 9.81? 735. So his weight is 735.75 newtons. Now taking this route along the hill, he reached to the top. It's the same thing if you climb straight up this 100 meters. This route probably much more than that, maybe like 150 meters. We don't know, we have to calculate. It is the same thing that going straight up 100 meters, instead of going at an angle 150 meters, you reach the same point. Let's say the guy is here and then he's climbing up 100 meters, same as taking this route 150 meters. So to go this 100 meters, he has to apply a force in the same direction, right? The force has to be in upward direction. How much force does he need? How many newtons? That is equals to his weight, or mg. So the amount of force you need to go up is equals to your weight, which is, so the force you need is 735.75 newtons. So what's the work? The work he has to do is force multiplied by the distance in the same direction. Or you can put the cos theta next to it also. So let me rewrite this: f d cosine theta. So force is 735.75, distance this way going 100 meters, cosine theta, the force and the distance or the displacement are parallel, they are in the same direction, so cos theta becomes 1, right? Theta is 0, cosine theta equals 1. So we have 7357.5 Newton meters or joules. This is the amount of work the person has to do. Now we can add a little discussion to this. If he had taken this route, let's say going up the hill like this, so this is the hill, the top of the hill, this is 100 meters, this is 150 meters. What we can do is we can figure out the angle theta here, assuming that this is a straight line, which is highly unlikely when it comes to hiking, right? You don't have like straight paths going up. There's always some kind of differences. But assuming it's a straight line, we can get here's the weight, here's the mg sine theta. So the force going up has to be equals to this. That force multiplied by this distance of 150 meters should give you the same amount of work. But don't worry about it right now, right? This piece. The beauty of this work approach is that it doesn't matter, most of the time it doesn't matter what path you take. There are specific examples, it does matter on the path, but it mostly depends on the starting point and the end point. So in this case, you start here, ended up here, it's same as covering the distance straight up, right? So force times distance gives you work. Okay, so let's move on. So let me clear the screen. So this next small topic is only for, others also can listen to this, no problem with that, but needed for the university physics class only, right? So this is the scalar product of two vectors. Scalar product. You guys know what scalar product is. If you have two vectors, vector A and vector B, vectors are indicated by this little hat on top of the letter. So the scalar product or the dot product, right? Dot product. A dot B is given by AB cosine theta. So when it comes to work, we multiply force with displacement in this manner. force times displacement cosine theta. So this is the same thing like the dot product, right? So we define the work, because of this similarity we define the work as F dot D, the dot product of force and displacement. Okay, so we will try some specific examples like this in class, but I want you to have this idea. Work can be defined as the dot product of force and displacement. Okay, all right, moving on. Okay, so we talk about couple of examples. One was the box being pulled to the side. So let's try this example. Let's say this is a 50 kilogram box. You apply a force of 20 newtons and move it a distance of, I think what I gave you was 10 meters, right? So again, let's assume there's no friction, so it doesn't matter what the mass of the box. This can be 5,000 kilograms. Still, if you apply 20 newtons, you can move it, and the work you do is 20 times 10, which is equals to 200 joules or Newton meters. Bigger the box, it will take more time for you to move it because it's going to move slowly. Lighter the box, more acceleration you get, it moves faster, you end up having higher speed at the end. But we are not concerned about any of those right now. What we need to find is the amount of work, how many joules you are spending, so that simply force times displacement. The dot just multiply them, right? Since they're in the same direction, you don't have to worry about the cosine theta. Now if the same thing, if we apply this 20, let's say with 60-degree angle, and you move it a distance of 10 newtons, 10 meters, this is meters. Now how much work do you do? So we get, we need work is FD cosine theta, which is 20 times 10 times cosine 60. Cosine 60 is half, 0.5, so you get 100 joules. So in these two cases, the second one, does it look like you have spent less energy? No, you are still spending the same amount of energy, but most of the energy kind of goes away because most of your force is being wasted. Only a fraction, only half of the force goes in the desired direction. So the amount of good work you did is 100 joules. So if you compare this 1 and 2, over here the object will be moving at a much higher velocity. It will reach this point faster, quicker. Over here it will be moving at a smaller velocity. It will take more time for you to get here. You will be spending the same amount of force all this time. So you are wasting this, you are spending the same amount, but the amount of actual work you did is less, right? So that's where the comparison, that's how we compare the two situations. You end up, it'll bring you to the same spot, but it will take more time and the speed will be less. Okay, so the third type of example is either climbing up, or you can say lifting something. So here we have the box and 50 kilograms. Now you try to lift it. With 20 newtons, you're going to lift it to a height of 5 meters. What is the amount of work you do? Work equals force times distance. The force you apply, 20 newtons, multiplied by distance 5 meters. Let me make it 6, so there's no confusion with the previous problem. 6 meters. So 120 Newton meters. Is this real? This is a fake example. You can't lift it with 20 newtons. This is 50 kilograms. Now the amount of force you apply really matters. Over here, because there is no friction, it didn't matter. Now you can't do anything with this 20. You have to first figure out how much force you need, right? So weight mg, my legendary example, 490.5 newtons. So you need to apply at least that amount. At least. If you apply more than that, you can lift it and accelerate it. Two things. So let's say you apply the same amount, or you apply 500 newtons. Right? So this is wrong. You apply 500 newtons, guaranteed you can lift it. So how much work you do? Work equals force, distance, cosine theta, 500, 6 meters. It's in the same direction, so cos theta becomes 1. So answer is 3000 joules, right? The amount of work you do is 3000. If you apply the exact amount, 490.5, you can still lift it. It will move 6 meters, but it will be a slow, constant velocity process. Right? You are just overcoming the weight, so you can't accelerate. It's going to be a very slow process. Hard to determine how much time it's going to take. But it will be little less work. It won't be 3000. It will be 2900 maybe, something like that. But the more force you apply, more work you do, but the job will be done faster. You will reach faster. It will take less time. It will be accelerating. It will have higher speed at the end. All right. So those are the things to keep in mind. Okay. So moving on, clearing all this. So all these examples we discuss with constant force, right? The force didn't change. We apply 20 Newton this way, it remained 20 all the time. We applied 500 newtons to lift it, it remained as 500. We didn't change the force. So these are constant force examples. And then work is simply that constant force multiplied by distance times cosine theta. If you draw a graph, the distance versus force, what do you think it's going to look like? Like for an example, this one. Right, starting from here, you moved it to this place, A to B. Let's say 10 meters, applying a 20 Newton force, a constant force. So the distance starting from 0, 10 meters, force remains constant at 20 newtons, right? This is newtons, this is meters. Force remains constant at 20. Now what about the area of this graph? This is a rectangle. So how do you find the area? Area is, you multiply the two sides, right? This side is 10, this side is 20. So 10 times, or you can say 20 times 10 gives you 200. The significance of this area is actually, if you think about it, this is your force, this is your distance. This is 200, which is work. Right? So area is the work. If you draw a distance versus a force versus distance, again, it's not force versus time, right? We used to draw a lot of graphs with time. This time we take distance as our x-axis and force as the y-axis. You plot the graph, you calculate the area gives you the work. Okay? So for constant forces, it's gonna be a constant horizontal line.